Okay, I asked my Stats 21 students this same question. Well, all right. Well, first of all, happy Monday and happy week 8. It's been a long quarter. I don't know. I don't know what's been going on. This quarter's been rough for me. Anyway, I just want to kind of check in with you guys, see how you guys are doing. See, it's a little bit awkward asking, but a lot of times, at least when we're in person, I kind of just chit chat before class begins or at the first few minutes of class to kind of just get a sense and feel for how students are doing. It's a lot harder when we're online and we're doing things over Zoom. But I just kind of wanted to check in, see how you guys are feeling. If you have any kind of concerns or worries, especially with this class in particular. I have to apologize. I know we are behind on grading. We've got homework 1 and homework 2 graded, but homework 3 hasn't been graded. Homework 4 hasn't been graded. Midterm 1 still hasn't been graded. And I'm really embarrassed about that. And then, obviously we still have to grade midterm 2. So I sincerely apologize. I think this week I'll have to really buckle down and try to get as much grading done as possible. Just so you guys can kind of get a sense of where you stand. But my hope is that, well, if I'll tell the graders to be kind of generous as far as grading the homeworks go. So as long as you've kind of been doing your homeworks and submitting them, hopefully you'll at least get most of the points. Obviously if things are wrong, we can't give you 100%, but I'll tell them to grade generously. And I don't know, I hope the workload has felt reasonable or acceptable. But I know, this quarter it's been, well, at least for me, I've just been struggling with, I don't know, whatever. It just feels harder to stay on top of things this quarter for some reason. So, but anyway, if you guys have feedback or questions or concerns, feel free to put them in the chat or unmute yourself or whatnot. I hope you feel okay, but if not, let me know and we can try to improve things. I know there's only a few weeks remaining. Your other classes, are they going okay? Maybe? Kind of? Okay, I see some pain grimaces. Oh, I got a thumbs up. Well, that's good. All right, well, for everybody else, I hope it's all right. Okay, well, at least, well, I don't know. I'm always excited about the material that we cover in this class. So I don't know if that's been exciting. Like I always think like kind of some of these machine learning things and like the classification and the clustering, like, well, we're talking clustering today and the neural networks. I hope at least the topics have been kind of neat to see. So maybe, okay. Well, today we're gonna talk clustering, okay? And so, clustering is what we call is a topic that's under the umbrella of unsupervised learning. Okay, so everything so far that we've been doing has been supervised learning. Okay, and supervised learning is the idea that there's an answer. There's an answer, and you want to try to predict the answer. And when you train your model, you give it known inputs with known answers, and you say this model's doing good because, or doing well because we gave it these inputs and the answers it gives us are very close to the known answers, all right? Or the target values, whatever it is that we're looking for, okay? So, we're able to measure things like the loss, okay? When you have supervised learning, neural networks, we try to train our neural network to minimize the loss, minimize the cost function. With classification, you're still trying to minimize the loss, which is basically the difference between what your model predicted and what the actual target values were, okay? On the other hand, we're gonna enter this kind of topic of unsupervised learning. And in unsupervised learning, we do not have target values, okay? And we're just kind of loosely, arbitrarily searching for structures that exist in the input values. You have data coming in and you're looking for some kind of structure, right? And so there are, just broadly speaking, and at least the two kinds of topics that we're going to focus on as far as unsupervised learning goes will be clustering, which is the idea of taking observations and grouping them together. And the other will be dimension reduction, which will be kind of reducing redundant predictor variables and things like that. And so we'll see dimension reduction when we look at PCA, principal components analysis. Today, I guess mostly this week, we'll look at clustering, and next week we'll also we'll introduce the EM algorithm, and that those are used for kind of clustering purposes as well. All right, and so the idea with clustering is that we have observations, and we want to group similar observations together, right? And observations that are not similar, we put in different groups, right? This is like a tough problem, because how do you define what it means to be similar, right? What does it mean to be similar? And that's going to be that's a tough thing to define. But how you define similar is going to be ultimately determine how you're going to group things together, right? Applications of clustering, you got all kinds of stuff. You can try doing like a document clustering, which is going to take different documents and try to put similar ones together. You can group physical locations together. So, if you take Uber or Lyft, there's often some kind of pool option where it pairs you up or groups you with other people who have similar routes and destinations, and it tries to make more money off of you by charging, by being able to charge multiple riders, but paying just the driver one time and stuff. So anyway, there's applications for clustering. Okay. Also, even kind of like product recommendations. So I didn't put this, but I'm sure you all have the experience where you've shopped on Amazon and maybe you bought, I don't know, you bought a pan, okay? And then Amazon's like, oh, do you want to buy this pan? And do you want to buy this pan? And do you want to buy this pan? Because, in their system, they have, they grouped these products together, and they said, customers who made this purchase have also looked at these products and things like that, right? And so, who knows? I suppose you might want to have an army of frying pans. Most people probably have a couple, but whatever. Okay, so today we're going to look at k-means clustering. Okay, and this is a simple clustering algorithm, and the way we're going to define what objects are similar is we're going to use Euclidean distance, right? And so just the fact that we're using Euclidean distance means we can really only the data that comes in is going to be numeric in nature, right? Because you have if you have two-dimensional data, you can kind of plot them, and it has to be numeric in order to do these things. It's rather difficult, or it's not easy to cluster data with categorical variables, okay? Because the categorical variable already kind of clusters or segments the data into different groups already as it is. And unless you have outside knowledge about the categories, it's difficult to talk about how similar these different categories are, right? So for example, if you wanted to, let's say you were looking at cars and what the exterior color is, okay? And you have you can get a white car, a gray car, silver car, black car, maybe a red car or a blue car or things like that, okay? Can you cluster these together? And, somebody needs to be able to say, you know what? These different shades of silver and gray, because you have different shades of cards, they're kind of similar. And, maybe, sometimes there's these exotic colored cars, right? Like a bright yellow car, or neon green car or something. And we'll say, these cars are kind of similar. We're going to cluster these things together. But you need somebody on the outside to kind of designate different categories being similar. And just kind of internally, if you just have categorical variables, most algorithms will have no idea how to cluster any kind of categorical variable. So a lot of these examples, we're just going to be looking at numeric variables, which is a limitation, because a lot of times when you look at data in the real world, there's going to be a lot of categorical variables. And so that definitely is difficult. And so, there's different ideas and things that are beyond the scope of this course, as far as taking categorical variables and turning them into numeric variables. And your simple and standard ones of taking them into making dummy variables out of them is not always the best idea. Okay, but anyway, let's get back to k-means clustering. Okay, so important, don't mix up k-means with k-n. Okay, they both have the letter k, and they kind of sound similar, but they're different. All right. So k-means clustering is an unsupervised clustering method. k-n is supervised, and it's a classification method. Okay. K-means is going to be an iterative algorithm. k-n is all done in kind of one shot, right? You just you measure all of the distances at once, and you just count which ones are closest. Okay. The similarities are you're using Euclidean distance, and there's a k. Okay, but that's what we have. Okay, so here we're going to define our clusters based on centroids. Okay, the centroid is basically the mean of the points that are assigned to that particular cluster. Okay, so if we say there's some cluster little k, the centroid of that cluster is going to be mu sub k, right? And we're going to say mu sub k is the mean of all of the points that belong to that, okay? And so what we're going to do is we're going to have some indicator variable, z sub nk. Z sub nk is a 1 if object n belongs to cluster k, and if object n does not belong to cluster k, it's a 0, okay? And so basically, the formula is sum of znk times xn divided by sum of znk. This seems a lot more fancy than, or I don't know, maybe it's not that complicated, but basically you're only adding the xn's if that n belongs to this cluster k, okay? And basically when it does, this is a 1, and this increments by 1, and when it doesn't, this is a 0, so it's not being added in. Okay, we have a question that says, could you use the median instead of the mean if you're worried about outliers because of Euclidean distance as a valid clustering method? There is something called k-median clustering and k-meteoroids clustering. And yes, you can use the median, except when you use the median as a way to measure the center, you often will use the Manhattan distance, because that Manhattan distance, as in the sum of the individual components, works out a little bit better than using the Euclidean distance and stuff. So yes, the answer is yes, you can do these things. There's also k-meteoroids clustering, which you're searching for what's called the meteoroid, which is an observation that is supposed to be representative of the cluster, the group cluster. So right here, this is a tangent. The centroid is just a central location, not necessarily one of the points that exist inside your data set, right? It's the coordinates of the centroid don't necessarily have to be any one of the data points. And so you have other algorithms that say, rather than a centroid, we're looking for what's called a meteoroid. And it says this observation, this one person or this thing that actually exists in your data is going to be the representative of that centroid, okay? Okay, over here, what exactly is the denominator like what does this mean exactly? Okay, so basically, let's say there are 5 observations. Let's say there's, you got 20 observations in your data set. 5 of them are assigned to cluster K. So your first cluster, there's 5 objects, 5 observations assigned there, okay? So Z and K is going to be equal to 1 for 5 of these objects, and it's going to be 0 for everything else. So the sum of Z and K in the denominator is going to be 5. And then, and the sum of the numerator will be only, will basically be the sum of the xn's for those 5 observations. The other 15 observations where the Z and K is 0, those are going to be zeroed out and they're not going to add up. So basically this mean here is going to be the mean of the 5 observations that belong to cluster K. We'll do some examples and I hope it makes better sense there. Okay, so this is the, this is how the algorithm goes, okay? Step 0, determine how many clusters you're going to search for. This is non-trivial, but we're going to just say there's not an answer right now that just says this is always going to be the best number of clusters. So first you got to decide. This is kind of a meta parameter that you have to decide. All right, and then there's some discussion about when the random assignment should happen, but as far as we're going to say we're going to randomly assign your points to each of the clusters at the first step. And then once all of the values have been assigned to a cluster randomly, you're going to calculate the centroid of the values in each of these clusters. So you calculate the centroids, and then you iterate, and you're going to reassign all of the values in your data to a cluster by associating that data point to the nearest centroid, okay? Using Euclidean distance. Using Euclidean distance, you assign that data point to the nearest centroid. And you're going to iterate. You're going to repeat this step of, once you've assigned everything, calculate the new centroids. Once you have the new centroids, you're going to calculate which centroid is the closest and assign the points accordingly. And you're going to keep doing this until no values get reassigned to a new cluster. Okay, so here is a very silly example. I've got 8 points, and we're going to say, let's search for 2 clusters. Okay, and so this is completely silly because I can just look at this and my eyes say, oh, there's a cluster here and there's a cluster here. Okay, but what we're going to do is we're going to run the k-means clustering algorithm and just show how this works. Okay, before I do that though, let me give you your first view quiz answer. Your first view quiz answer today is E. E as in elephant. E as in elephant is your first view quiz answer. Okay, so here are our 8 points in the data. And step 0 is determine how many clusters we're going to search for. So we're going to say we're going to search for 2 clusters, okay? And then we're going to start by just randomly assigning points to a cluster, okay? And so here, I'm just going to randomly sample values 1 and 2, okay? And those will be on my assignments. And then Z will be 0 or 1. So we're going to just say assignments equal to 1. That's going to be a true or false value. And if we do as.integer, trues will become 1 and false will become 0. So we got Z1 for if that point is assigned to cluster 1, Z2 if that point is assigned to cluster 2. Excuse me. Okay, so let's go ahead and take a look here. And so here I just randomly assigned some points. 3 points got assigned to the cluster represented with the black dots, and I have 5 points assigned to the cluster represented with the red dots. Okay, and that's fine. I didn't get an even split as far as the assignment goes, and that's okay. Doesn't always happen. All right. Okay, and so if we look at the coordinates, so these are the coordinates. I got 0, 0, 1, 0, 0, 1, 1, 1. Over here, I got 3, 3, 4, 3, 3, 4, and 4, 4. And so we've got 0, 0 currently the point 0, is in the black cluster, okay? And so it's assigned to cluster 1, and so its Z1 value is a 1, and its Z2 value is a 0, okay? Point 0, 1, I'm sorry, 1, 0, this point, also 0, 1, these got assigned to the red cluster, okay? And so 0, 1, and 1, 0 got assigned to the red cluster, which is assignment 2. And so their Z1 values are 0, and their Z2 values are 1, okay? And so this is how it goes for all 8 points. And we can see that the column Z1, there's 3 values that were assigned to column Z1, cluster 1, and we can see there's 5 values assigned to cluster 2. Okay, and so what we're going to do is we're going to calculate the centroid of cluster 1. Okay, so the centroid of cluster 1, we're going to say, all right, we have 3 points assigned to cluster 1, and as far as the x1 coordinate goes, we have a 0, we have a 1, and we have a 4. Okay, so we're going to add 0, 1, 4. We add those up, we divide by 3, and its coordinate is 1.667. And coincidentally, as far as these data points go, for the x2 coordinates, those coordinates are also 0, 1, and 4. And so it's x2 is also 0, 1, 4 divided by 3, 1.667. It's just a coincidence of this data that that we happen to have the same centroid there, okay, or the same x1 and x2 coordinate. We look at x2 and we have 5 data points, okay? The 5 data points in x2 for x1, we have 0, like if I multiply x1 by z2, we would get 0 plus 1 plus 3 plus 3 plus 4, 0, 1, 3, 3, 4, divide by 5, I get 2.2. I do the same thing for x2, and I also get 2.2 there. Is that okay as far as calculating the mean of the x1 and the mean of the x2 coordinates for these 2 clusters, okay? I could have also done this using something like dplyr or whatever. You know, you can use an apply function as well to kind of calculate these things. Totally, there's lots of ways to calculate what the mean of x1 and mean of x2 are for each of these things, okay? So here I'm gonna just say, I just dplyr, and I said group by the assignments, which is either assignment 1 or assignment 2, and we're going to calculate the mean of x1 and the mean of x2. All right, and so here are the centroids that come out: 1.67, 2.2. Okay, and so this is it. The mean of the 3 black dots is right here. The mean of the 5 red dots is right there. That's the centroid. So now that I've calculated the centroids, the next step is you're going to take each point and you're going to measure the Euclidean distance from this point to the 2 centroids, and you're going to assign that point to whichever cluster is closer, whichever centroid is closer. So this first point is at 0, 0, and we say which centroid is closer, the black centroid or the red centroid? The black one is, okay? So that gets assigned to black. Okay, the next point, 0, 1, which one's closer, black or red? Black is closer, it gets assigned there. What about this centroid? 1, 0, black or red, which one's closer? Black is closer. So all 4 of these points, the black centroid was closer, so they get assigned there. Okay, what about this one? This one's 0.33. Okay, which centroid is closer? The red centroid is closer, so it gets assigned to red. And we calculate the distance to the red and the black cluster for this, or red and black centroid, and we say which one's closer. And so for all 4 of these, the red centroid is closer. And so this is our point assignments after reassigning them. And then what we do is we recalculate the centroids. We say, what's the centroid of the points assigned to the black cluster? What's the centroid of the points assigned to the red cluster? Okay, the centroid of these 4 points in the black cluster will be 0.5, 0.5. Over here will be 3.5, 3.5. Okay, and we do that. Okay, and then we do this, and then technically we can do one more iteration, and we can say, all right, let's just make sure. Let's go through and reassign points. And if we reassign points, we're going to see that none of these points get reassigned. All 4 points over here will remain in the black cluster, All 4 points over here will remain in the red cluster. None of the points will get reassigned. And we will say this has converged. And so this will be the clusters, and that is it. Okay, does that make sense as far as how that goes? All right, let's go ahead and try this out with a slightly bigger data set, okay? And so here I generated data in, I generated 3 clusters of data, and these are multivariate normal data sets, okay? In two variables, x1 and x2. And we'll go ahead and see if we can discover kind of the 3 original clusters here, okay? So we start off and we say, how many clusters are you searching for? So again, when the data comes in, everything is unlabeled. There's no labels, okay? And we're gonna say, how many clusters are you searching for? And we're gonna say, I'm searching for 3 clusters. And we just randomly assign each point to one of the 3 clusters. So we just randomly say some points are gonna get assigned to black, some will get assigned to red, some will get assigned to green. Those are kind of the 3 starting colors here. You know, I realized red and green are not good colors for somebody who has color blindness. So I apologize for using red and green. Maybe I'll go back and I'll fix these to switch to red and blue or something. Okay, but we just randomly assign these to 3 clusters here. And I calculate the centroids, okay? Now, I've kind of obfuscated my code here because this is gonna be in your next homework assignment. So your next homework assignment, you'll be doing this kind of stuff. I don't know, how did the last homework with the classification, how do you feel like that went as far as, went good? Okay, great. Well, this should be similarly, well, the EM is, I don't know, maybe a little bit harder, but we'll see. Okay, so anyway, I calculate the centroids, right? I say, all right, what's the centroid of all of the black dots? What's the centroid of all of the red dots? What's the centroid of all of the green dots? Okay, and this is what we get. And, you know, as we might expect, there's not a whole lot of difference between these things. But again, just because of random assignment, they're not all exactly the same, and that's fine, all right? So these are the 3, the centroid of the 3 colors are right here, okay? But even then, there's just enough variation where we can say, all right, which ones, when we say which centroid is the closest, one of these centroids will be closer than some of the others, right? So we go through and we're gonna say, you know, basically all of the points over here, we say which centroid's the closest, the red one's gonna be the closest. All of the points over here, we say which centroid is the closest, the green one's gonna be the closest, okay? So which dots will have the black centroid the closest? Only a small few, right? If we look at where this black centroid is, it's underneath this red dot here. So like this one, these points here will be closer to the black centroid. I don't know, maybe, I'm not sure. I think only just a few points right here, okay? But as soon as I get over here, which one's closer? You know, the red one edges out the black one just a tiny bit, okay? So we're gonna go through every single data point and we assign the dots to each centroid accordingly, okay? And so this is what we get, okay? So all of these points got assigned to green, all of these points got assigned to red, and these ones got assigned to black, okay? It is possible, it shouldn't happen, but it is possible that after reassignment, one of the clusters ends up with 0, okay? 0 points assigned to it. And if that happens, you know, when you say, you say search for 3 clusters, you end up getting a solution with only 2 clusters found. That could happen. I would say that that's fairly rare. You can just redo it with a different starting seed, and you'll probably end up with 3 clusters in the result. But, you know, sometimes weird things happen where, you know, one of the clusters you're searching for just kind of disappears into either a single point or something where none of the clusters get assigned. Okay, but anyway, we still have just a few dots assigned to the black cluster, and that will keep it alive, okay? And all of these, so we should say, okay, here are all the red dots. what's the centroid of all of these red dots? It's probably going to be somewhere around here. What's the centroid of all of these green dots? Somewhere around here. What's the centroid of all of these black dots? Somewhere around here, okay? And so we do that, and this is what we end up getting. We say, what's the centroid of all of these, of the dots assigned to each of the colors? Okay, and now we reevaluate we reassign points to each centroid, okay? So as far as the red dots go, or as far as these points over here, red is the closest. But now if we look at these points, like this point right here, it's closer to the black centroid, right? And these points right here, it's closer to the black centroid than the green ones, right? And so you kind of have like a, you know, there's going to be some kind of, where's my drawing tool? Okay. Some kind of partition here that, you know, somewhere around here, I can't draw a line here, huh? Okay, well, anyway, some kind of line that separates red from black here, some kind of line that's going to separate green from black over here. So you can kind of like draw a line that connects green and black here, and then halfway through, draw a line perpendicular to that, and that will kind of be the boundary that separates green and black. Okay, and so if you do that, this is what we get after we reassign points to each centroid. Okay, and now so I have these dots assigned to the black centroid, these dots assigned to the green centroid, these dots assigned to the red centroid. We recalculate the centroid of these points. Okay, so if I do that, the centroid of these assignments end up here, and so they move, and then we redo the process. We iterate and we say, all right, where do these dots go? Okay, and so we can see, all right, you know, this dot right here is closer to the black centroid than it is the red centroid, so it's going to get reassigned. Okay, so we reassign points again, and this is what we end up having. And then we recalculate the centroids, and they shift, and they go here. We repeat the process, and I think this one might get assigned to black. This one's a close call. I think it's going to stay red. Let's see. Oh, it gets reassigned to black. Okay. And as far as these ones, I think these ones will go to black. No, they remain. Okay. Oops. It says no changes means it's converged. No, there were changes. Okay, sorry. I should probably have one more slide here that just says there actually were changes between this slide and this slide. Sorry. Okay, when there's no more changes, that means it's converged. And so this is going to be the, I think if I did it one more time, there would be no changes. And if there's no changes, then the assignments have converged, and that will be our solution. We'll say when you search for 3 clusters, this is what it finds. Okay. Now, the labels of the clusters are completely arbitrary, and they just happen to line up with our original assignments. And in this case, we're kind of cheating because we generated the data, and when I generated the data, I generated kind of 3 clusters of data, so I kind of knew the answers. So if I compare what k-means clustering finds versus kind of the original things, you know, most of them kind of ended up in the correct cluster. But again, just from in the random generation process, this red dot ended up kind of far away. It's a bit of an outlier compared to the other dots here. And this black dot is a tiny bit of an outlier compared to the other black dots. And so this dot at the k-means clustering ends up in the red cluster, and this dot ends up in the black cluster, okay? But there's no way to know that, and that's gonna just happen, okay? There is a function in R called k-means, right? There's a function in R that does KNN. There's a function in R that does k-means clustering, okay? So again, you're gonna be writing code to do k-means clustering, and I think it's a good exercise to kind of learn some stuff as part of your homework. But again, in production settings, you're not gonna be using your own kind of k-means clustering code that you've written. There's these things that have been written in R, they work very well, okay? And so when you run, you can just take the same data and throw it into k-means clustering in R and say you want to look for 3 clusters. It's very simple. You just say, I want to do k-means on this data set, look for 3 clusters, and it's going to create results, all right? And you can just kind of plot the results, and you can say, I want to color by the colors found, or the clusters found in the results, and it does this, okay? Let me give you your second view quiz answer. Second view quiz answer today is A as an apple. A as an apple is your second view quiz answer today. A as an apple, okay. So one thing you might notice is in this thing, when I run k-means clustering, the green dots ended up over here and the red dots ended up over here, okay? And when I did this, they ended up like this, and over here, they ended up like this, okay? The thing about clusters and clustering algorithms is that the labels are completely arbitrary, okay? And so it's fine. This solution is just as valid as this solution and is equally correct, okay? It's just, let's say you're basically forming the same groups. It's just one person labeled these groups 1, 2, 3, and somebody else labeled them, the same groups, groups A, B, A, C, or something like that, okay? And so it's just, you end up with the same groups. You ended up clustering and putting kind of the same observations together. It's just, what label you gave them has changed. But again, this is just, the labels are completely arbitrary. And so it's not wrong. It's not wrong. And so this is something, it's known as the label switching problem. It can produce some headaches for some people as far as, if you do multiple trials, it might seemingly at first glance seem like you're getting like wildly different results, but you're actually getting, very similar results, okay? But that's an issue, okay? All right, so this is k-means clustering in R. You just run k-means and it works. Okay, when you look at the results, right? If you print out all of the results from k-means, it gives you the means of the 3 clusters. It gives you the clustering vector, okay? And in my original data, all of the 1s were up front, and then there were all 2s and then all 3s. And so we can see we kind of got the same things, maybe this one as far as the generating point, it got assigned over here. And we can also just see just arbitrarily, instead of labeling them 1, 2, 3, I went 1, 3, 2. Again, not a sign that the answer is wrong, just the labels again are arbitrary, okay? There's a few other things. One thing about k-means clustering is that it is actually, the solution that it finds will minimize the sum of squares, the difference between, you have a within sum of squares. So within a cluster, if we say, what's the distance to your own group centroid versus what's the distance to the kind of the grand centroid. So if there were no clusters formed at all, and we found the centroid of all of the points, that would be the total, that's the total sum of squares there. And whereas when you calculate the distances to each kind of your own group, that we want to minimize that, right? And so the between group and versus the groups within, that sum of squares is a lot smaller versus the outside. And so we're finding kind of a reduction of 86.2% from distances to the grand centroid, if that's what we can call it, versus distances within each group. Okay, so by the variation within each group is only like 14% of what it was compared to everything. Okay, and so you have some different things that you can find, the within SS versus the between SS and total sum of squares distances. Okay, and so all of these are stored in a list and things like that. Okay, all right, let me just show you what happens if we mess around and we say, let's search for, quote, the wrong number of clusters, all right? So when we generated our data, we actually, I generated data from 3 distinct groups, okay? And you think about, if we think about like, why would we even want to cluster in the first place? When we do clustering, we believe there's like kind of different categories of either people or preferences or whatever it might be, right? So if like people on Netflix were looking at your video, watch history, they might say like, oh, you're a person who likes these types of movies, and therefore we're recommending these things, right? You go on YouTube and you get all of these recommended things. They say, oh, you watch these other things, we're going to recommend these videos to you. And they're basically saying, we can kind of, there's something that groups these things together. And that's a hard question to say, well, how many groups are there? Okay, so let's just try out searching for clusters, different numbers of clusters. So here, if I take the same data and I say, let's search for 2 clusters, this is kind of the solution that it arrives at, okay? If I say search for 4 clusters, this is one possible solution that it arrives at. And so we get this cluster, which is red, this cluster, which is green, and this cluster, which is blue, and this cluster, which is black, okay? If I ran this again, same data, but just with kind of a different starting point, and I say search for 4 clusters, it ends up with different results, okay? We get 1 cluster here, 1 cluster here, but this middle part got separated into a cluster up here and a cluster down here, okay? So compare this versus this. And again, the colors themselves, but the individual clusters are a little bit of what's more interesting, did similar points. So this cluster seems like it remained kind of the same. So if we look at the points over here and the points over here, that seems pretty similar. But if we look at these points over here, the assignments definitely changed. Okay. And so, what gives? How does this work? And the answer is, how many clusters you should search for is almost an impossible question. It's almost an impossible question to answer well, unless you have outside knowledge of the data itself, right? So for example, just to show you how difficult it is, let's say you were creating some kind of survey form, a demographic survey form, where you're doing, let's say you work for the Census Bureau for the government, and you need to come up with how many categories should we have for race/ethnicity, okay? This is really hard to answer, right? So you could just say, well, somebody could say, oh, you know what, there's only 1 race, the human race. And that's a correct answer, okay? In the US, we can just say, we can also say, in the US, we can look for 2 kind of races, and we can say white versus non-white, or person of color. That's kind of a split that's possible. We could look for 3, and we can say, white, black, and other. 4, 4 or 5, and you might say we can have a category for Asian, Pacific Islander, and further, that could be split further into more, right? So among Asian, you can split that further into Pacific Islander, East Asian, Southeast Asian, South Asian. Even among, like, say, East Asian, that can get split further into, like Chinese, Japanese, Korean, and there's no end, right? Like, you can always kind of take the number of clusters you have and say, you know what, we can further cluster, we can further separate and divide these into even more categories. And it's truly, it's a very difficult and close to impossible thing to really answer and say, this is the definitive number of clusters, or the definitive number of groupings of people or objects or whatever it is that you're looking for. And so, we have a few ways to kind of help us, but these tools are no match to just kind of thinking and reasoning, right? And certainly a lot of times in your data, if you just follow some kind of algorithm that says, oh, this is the number of clusters you can pick, you're often, especially if you're dealing with people, you might often leave out some kind of marginalized group, right? So, the data set that you're looking for just says, oh, you know what, this is really small, so just we'll just ignore this, right? And if you just apply this blindly, that could end up happening. But you might realize, like, these are people that there might not be a lot of them, but their needs and their things are very distinct from everyone else, and it's not right to just kind of ignore or put them in the same group as everyone else. It's really hard, and so you need to have somebody kind of familiar with whatever thing that you're looking at to inform how these decisions should be made. But again, this is just completely made up data where we're just going to say, all right, how could we go about searching for some kind of number of clusters in some automated way? One possible solution is you just say, all right, we're going to search for 1 cluster, 2 clusters, 3 clusters, up to 10 clusters, or however many clusters you're going to look for. And then we're going to just repeatedly run 20 times. What are the solutions you find when you look for 1 cluster? What are the solutions you find when you look for 2 clusters? What are the solutions you find when you look for 3 clusters? What are the solutions you find when you look for 4 clusters? Okay, and we can see, all right, what kind of results do we get, right? And so when you look for 1 cluster, which is kind of silly, because you're going to get the exact same results every single time. You're going to put everybody into 1 cluster. So there's going to be no variation, okay? When we looked for 2 clusters, we also ended up with no variation in terms of the amount of, we're looking at the within sum of squares. We're seeing no variation in the within sum of squares, okay? But when we look at things like 9 clusters and 10 clusters, the solutions that we get when we looked at 10 clusters, we're getting some variation. One time when we did 10 clusters, we got 258 for the within sum of squares. One time when we did 10 clusters, we got 230. Another time when we did 10 clusters, we got 244. And so so we're getting variation, different kinds of results. Here, when we did 10 clusters and we got 330. So we can kind of take a look at how much variation there is when you search for a certain number of clusters. Okay, and so you can also kind of plot that using some box plots. So going from 1 to 2, and effectively we see kind of a common thing is that as you search for more and more clusters and you make your model kind of more and more complicated, there's going to be a reduction in the within sum of squares that you find, okay? And so you kind of look at this and you say, all right, where is the change in within sum of squares? Like, where does it kind of change and no longer benefit? So, kind of the biggest, there's a dramatic drop from 2 to 3, and then going from 3 to 4, 4 to 5, 5 to 6 doesn't seem like there's as much improvement. So you might say, well, let's search for 3 clusters, okay? But again, as you are doing some kind of problem, if you have outside knowledge, if you're familiar with the subject matter, I would say definitely use that as far as how many kind of clusters you're searching for, how many kinds of things that you're going to be looking for. Again, it's a difficult thing, and there's all of these problems have to be approached with a bit of nuance. So anyway, that's k-means clustering. Just a bunch of pictures as far as today's slides go, but the instructions, really the algorithm comes down to this. Okay. All right, let me go ahead and give you your last view quiz answer for today. The last view quiz answer for today is D. D as in dog. D as in dog. Okay, so we'll end here, and we'll see you guys on Wednesday. All right, have a good night.